Now I want to summarize the factors that affect the period of simple harmonic motion. And this will only be partially effective just telling you, but that's all I'm going to do here. And you'll probably want to make sure that I demonstrate these things to you to prove it, so to speak. But if you're sufficiently satisfied with just a description, that's okay too, just to make sure that you have the knowledge in case you don't have the opportunity to see this. But for the spring mass system, oscillating back and forth, there are several things that we can do. We can change the amplitude, and we see that it has no effect. So when you move it just a little bit, it oscillates with a certain period. And then when you instead stretch it a lot, it oscillates much bigger, in other words, larger amplitude, but the same period. So that seems a little strange, but considering that the further you stretch it, the greater the acceleration is, it actually whips real fast through that equilibrium position, and the period stays constant. So that's really an amazing thing. It's not just close, it's exactly the same. Now, what about mass? We put more mass on this thing as the object that's being oscillated back and forth. As the mass goes up, the period goes up, because when you make more mass move with the same amount of force, you have more inertia, and so it's more sluggish, right? So it takes longer to move the object with a bigger mass. So that's pretty commonsensical, I believe. What about the spring stiffness? So as K increases, now as K increases, the spring is stiffer, so for a given stretch it's pulling harder, so it should whip back and forth faster, or the period should go down, because there's a larger restoring force for any given displacement. Having said that, I can give you a formula that's going to be consistent with what we just mentioned. No real derivation, just conceptual idea here at this point. That the period of spring is this formula. There it is. 2 pi square root of m over k. Now the 2 pi is not intuitive. And the fact that it's square root is probably not either, just from what I've said. But consider that proportional to m. In other words, as m gets larger, t gets larger. Oh yes, in fact it did. As k gets larger, it has a greater restoring force, goes through its period quicker. In other words, t gets smaller. Inverse relationship. So that makes sense. To see that it's the square root of those factors actually would require a little more theoretical work or experimental. And we can actually do both. Well, let's consider the pendulum. And for a pendulum, the size of the vibrations, okay, the amplitude, just like we did here, and we see that there's no effect. And yet there's a limitation here, because it turns out that a pendulum oscillating back and forth is not perfectly in the category of simple harmonic motion. It's an approximation. And so you're limited to small displacements, a small displacement angle, less than about 15 degrees, rule of thumb, and you have essentially SHM. As the angle gets much larger, we see that the amplitude gets larger then as well. I'm sorry, the period gets larger. When we make the amplitude really big with a pendulum, the period gets larger. And really, why? Because the restoring force is not proportional to the displacement when we make the amplitude really large. So that's the reason. Now what if we increase the mass? Now up here the mass made the period go up. Now we're going to put more mass on the pendulum, and we discovered it has no effect. Well, basically because what is the restoring force for the pendulum? Well, it is the gravitational tug on the mass. It's not the stretch of the spring in this case. There's no spring. So more mass, more inertia, but more force. No effect. Makes sense. Same reason why light objects and heavy objects fall at the same rate in a gravitational field. Now, what happens when you increase the length? The period goes up. So when you oscillate this thing back and forth, a real long period pendulum goes real slow, or if it's real short, it goes boop, 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 boop. And that's essentially it. And the reason? Because there's a longer path length. It's the same restoring force, basically, at the different angles, but longer path length for the longer pendulum. The spring system, when you increase the amplitude, for instance, you know, it had a greater force. The thing that makes this force greater for a pendulum is changing the angle, making a bigger angle, like we had here. But by changing the length, you know, the angle that this makes then with the vertical, you know, to get to the same angle as with a short one, you have to move it a longer distance. So the period goes up as the length goes up. And now this one, I can probably demonstrate this mildly, although not here. Acceleration of gravity. You think, well, that's a constant. Well, yes. But as gravity goes up, this probably should be intuitive. As gravity goes up, the restoring force on the pendulum goes up as well. So if the acceleration of gravity goes up, the restoring force goes up while inertia stays the same. So the period's going to go down. We have a larger restoring force. So here is a formula that's consistent with all that. Period of the pendulum, 2 pi square root of L over G. So again, you don't know the details of this by this explanation, but as length goes up, period goes up. We just discussed that. As gravitational field goes up, then the period goes down. All right, so it's all consistent with this. And there's the formulas. Now, summary of SHM. SHM is motion that traces the same path in equal time intervals. So it keeps doing the same path over and over in the same amount of time. The force and acceleration point toward the center or the equilibrium position of the SHM, and that force and acceleration is 0 at the center, but the center is where V is at a maximum value. And then the restoring force and the acceleration are maximum at the ends, and at the ends V is 0. So the force and acceleration are kind of like almost inverses of the velocity or the speed, or they switch roles at least at those extreme positions. And so our next step in the next video, we're going to start looking at the detail of SHM as it pertains to circular motion. We're going to use what's called the unit circle to trace the various physical quantities and see what sense we can make out of simple harmonic motion and how it relates to circular motion.